calculus problem. A cone-shaped, what's up? Yeah, Henry Chris. A cone-shaped drinking cup is made from a circular piece of paper, are you recording? Of radius r by cutting out a sector and joining the edges. Find the measure in radians of the angle to be cut out. Wait, I feel like I fixed up this problem at some point. Did I also like forget to include the picture?
Yes! Oh
yeah.
My gosh! I was complaining about mom about that. I was like, how do you say C figure and then no figure? It said C figure twice. I know!
C figure. I think I drew it in and then I somehow like was gonna, whatever.
And my mom was like, oh well, can't just
referred to the picture too.
I mean, it wasn't so
The hint
bad.
referred to the picture.
The hints kind of referred to the picture. I apologize, I realized that yesterday. I need to make an electronic. I drew a picture one year at the last minute, but that did not get, the description was fine. Yeah, you could draw your own damn picture. Alright, so, and we have an absolute stop time. Wait, stop talking. Al, stop talking to her. We have to stop and we have to start a new activity in like 4 minutes. So however far we get in this problem in 4 minutes, that's how far we get. Alright, a cone-shaped drinking cup is made from a circular piece of paper of radius big R by cutting out a sector and joining the edges. Alright, what is this about? We have a circle, and here's what we're going to do with this circle. We're going to cut a sector out of the circle. So a little bit of this, and a little bit of this. And the radius of this circle is big R. Man, if you guys didn't try this problem at all, I'm like really angry with you, because it's really, really hard and interesting and weird. Now I'm just telling you what to do. Rawr. This is why you have to do the homework on the actual day it's due. Rawr.
Not saying rawr.
Busis. The radius of this circle is big R, and what we are going to do is we're going to cut out a piece. Does everyone understand what's going on? You cut out the piece and then you like join it together to make a new figure, which then becomes three-dimensional, and then we can drink out of it. Well, the interesting question to ask is, how much do I have to cut out in order to make the volume of my cone as big as possible? And does everyone kind of see what's going on? If you cut out only a tiny bit, then when you join them together, your cone is not going to be very tall, right? But if you cut out a lot, the cone will be taller, but will be sort of like smaller, right? So there's some magical amount you can cut out for which the volume of the cone is maximum uses. I said in my description that though that is the reasonable question to ask, the algebra works out much nicer if you instead let theta refer to the angle to be kept. So let's do that. That's what I meant by that. So let's just call this angle theta.
Wait, which part are you cutting off?
What?
Which part are you making it cone?
I'm cutting out this, but I'm going to let theta refer to the amount of the cone remaining, which is
So
what.
I ignored what I thought your advice said.
Okay, good. You did it this way, right?
Yeah.
Yeah, that's the good
I
way.
thought your advice said the other way.
Okay, so what is the crucial understanding here? Well, okay, actually, it would be nice if we had a model of this. Oh, we do have a model of this because I made one. So here is the figure, and what we are going. Oops, I gave away something. Oh well. Here is the figure, and the radius of the cone is r, and that angle is theta. And does everyone kind of understand? And then, if you didn't get this before, you get it now, hopefully, which is that we glue it together, right? We glue it together, now suddenly we have a drinking cup. Okay, well, what we need to figure out is what is the length of this arc. And there is just a formula for the length of an arc of a circle. If I have an arc of a circle, let's call this big R and call this theta. What is the length of this arc? You guys just know this?
It's
R times theta. Alice, why?
It's like theta over 360.
Yeah, if we temporarily call that arc length x, then the length of that arc is to the length, Rabbi Fleischman, of the entire circumference, which is 2 pi r, as the angle theta is to the total number of radians in the circle, 2 pi. So the 2 pi's cancel from both sides, and we just get that x is theta r. What's up?
Big R.
Big R.
Oh, okay, yeah, sure. So the point is that I've now learned, using some pre-calc / geometry / common sense, that the length of this arc is r theta. And big R is going to be a constant throughout this entire problem. And the crucial observation without which you could not do the problem is the geometric connection between the dimensions of this circle and the dimensions of the cone. And if you either have a good imagination or you made a cone yourself or whatever, you came to this conclusion. What is the conclusion? Okay, what is the crucial connection between the geometry of that flat thing and the not flat thing?
Well, that's not flat. I mean, it's 3D.
Yeah, I know. What's the connection?
The surface area is this small.
Oh, okay, yeah, that's true. The lateral area of this cone. Okay, well, I guess maybe, Garrett, what do we try to maximize?
Trying to maximize the drinking, right? Like how much you can drink.
How much you could drink, otherwise known as?
The area.
Otherwise known as? The volume. Yeah, we're trying to maximize the volume. That is the entire point, right? Maximize volume. So I guess I need a formula for the volume of the cone. What is the formula for the volume of the cone? Mateo?
Like 1/3 pi r squared h.
Yeah, 1/3 pi r squared h. Then we have to be careful because this is not the same r, right? Because this is now I'm using little r. Little r is the radius of the cone, which is a difference, right? Okay, so wait, did you guys figure this out?
Yeah.
This is like the whole point of this problem is doing this step on your own. If you didn't do it on your own, I'm gonna say rar again. Ethan Chen.
Wait, so like 2 pi r of the cone is theta r?
Yes. Ethan Chen, crucial observation. The crucial observation is that the arc length of the sector that remains becomes the circumference of the base of the cone of water. Raise your hand if you realize that. Like you kind of like had to know that, or else you couldn't really do anything. Yeah, so the connection between all these is that, yeah, just like he said, r theta, the arc length of the sector, equals 2 pi r. And thus I can solve for everything in terms of theta if I want to, right? Thus this little r is just r theta over 2 pi. Okay, and then there's one more observation necessary. Yo.
R, well, like, there's like a Pythagorean relationship between like R, big R, little r, and h.
Yeah, right? That this big R becomes basically like the slant height of the cone, right? And so I can also express the height of the cone as a function of theta. The height of the cone is going to be, well, it's going to be root big R squared minus little r squared, right? Say right.
Right.
Yeah, and so if I wanted to, I could even, take this expression and like sub it in. Okay, so actually, this problem turns out to be easier if you don't substitute everything in for theta right at the beginning, but instead just do it all in terms of little r. So well, what is the volume? The volume is going to be pi over 3 times r squared h. Well, I can solve for h right there, so really this is just pi over 3 r squared root big R squared minus little r squared. This is a formula for volume in terms of little r. And no one says I can't just do the problem this way, right? Differentiate. Here I have constructed a function which expresses the volume in terms of little r, and now I can just maximize this with respect to r. This is the easy way to do it. Maximize with respect to little r. And if you will actually notice that I think it's the identical problem to like the previous problem, right? Does anyone know what I'm talking about?
Yeah.
Okay, then the two previous problems. This one.
Oh, yeah.
I think it ends up being, you did it kind of weird as usual, but is it the exact same function? Emma, it's the exact same function as in like the two problems back, right?
Yeah.
Yeah, so the way you finish this problem off is you do all this math, and you figure out the R value.
It's actually the same answer, I think.
It is. You get the same R. Yeah, it's the same because it's the same function.
It's just a rule you use is that you all for cones and cylinders that R squared that R equals half H.
I don't know what you're talking about. But yeah, there's probably some connection there. But anyway, you do this whole thing and you figure out what the R is, which maximizes the volume, and then you can go back and you can calculate. Once you have found that minimum R value, then you can calculate theta in terms of that. Did anybody get all the way to the bottom and you've got an actual theta? It ends up being about 60 degrees-ish, approximately. If you convert it to degrees. All right, that's all the time we got on this. How's this packet going, generally speaking, for you? Okay, Ethan says good. The rest of you catch up with him. All right. So put this away. Today's Thursday. Yeah, you're gonna finish it for homework. If you're kind of lost, if you're finding it hard, not just you but everybody, if you're finding this packet really, really hard, what should you do about that?
Math help.
Come into math help, for example, like tomorrow, or go back in time and come on Tuesday, which is what you should have done, all of you.
I did.
I know.
I was there also.
Good.
Only I brought my.
All right, Samin, bold new thing happening now. Put all this differentiation crap away. We're done with that. We are now doing something else.
Mr. Giles was telling us about it.
Yeah. This class is starting to get really, really good now. And in fact, as I warned Gabe, this class is entering the danger zone. Oh yeah, you too. This class is entering the danger zone, and you too, kind of. The danger zone means that every moment for the next 3.5 weeks is going to be filled with tension, excitement, foreboding. What are some other synonyms for that?
Sleep.
Suspense, excitement, panic, wonder, chaos. All right. We have been talking about differentiation for many months. What we are going to talk about right now is something called antidifferentiation.
Is that like backwards?
Anti-differentiation. And before someone does something terrible for which I will never forgive them, perhaps we should have another quick conversation about something that's not going to be happening. And what's not going to be happening is we're not going to be talking about the I word. What is the I word? I hesitate to even say it. In fact, I cannot say it. And in fact, if it uses, you need to leave the room. I'm not kidding. You need to leave the room.
Wait.
Think about it for a minute and then come back.
Wait.
Like right now, and you're wasting class time. Count to 10 and then come back. All right. So there is an I word, and this is the I word. It's blank.
Why aren't we allowed to?
Okay, shh.
My dad says
But
it all the
shh. We're not using this word. This is the verb form of the word. There's also. Okay, go get music.
Oh my gosh.
There's also a noun form of the word that we're also not going to use. There is also another form of the word, and there's even like another one. Okay, so very important over these next couple of weeks that we do things properly. And in order to do things properly, we have to not talk about crap if we don't understand it. And thus, class rule, we are not going to use the I word. And some students get confused and they say, Mr. Rose, what do you have against the I word? And you misunderstand me. I love the I word. I love it very, very much. I love it so much that I'm going to give it the respect that it deserves by waiting until the appropriate moment when we are ready. And when we are ready to use the I word, we will use the I word, and until then we will not. And that means that you cannot talk to anybody who might potentially know anything about this. That means you can't talk to any juniors, you can't talk to your parents, you can't talk to upperclassmen, you can't talk to Arun. Actually, he's approved, he's okay. He has self-control. You can talk to me, because I know what I'm doing. You can't, even Forster is not, no, what's his name? Who are our textbook? Larson. Even Larson is not to be trusted. For example, you will see this word at the title of the chapter that we're starting now. So there are enemies everywhere. It's like the Red Scare all over here. But anyway, they'll bring me over in a couple weeks. What's up?
You should go through them and just like black.
Okay, good. So now we will do a 45-minute lecture in 25 minutes. Let's do it. What is anti-differentiation? Okay. Well, here we go. F is an antiderivative. F is an antiderivative of little f on some interval, on an interval I, if and only if. So big F is an antiderivative of little f if, well, if the derivative of big F is little f. So if the derivative of big F is little f, then we say that f is the antiderivative of little f. And that should be true for all x on some interval. Okay, let's immediately go to an example. I give you some function, f of x equals x squared. Can you think of an antiderivative of that function? In other words, can you think of a function which, when differentiated, brings me back to x squared? Someone raise your hand if you've got one. Robbie Fleischman. Robbie says f of x equals x cubed over 3. Do we agree? Does that work? Yeah, it just does, right? Differentiated, what happens? You get back here. Robbie, how'd you come up with that? Just say duh.
Duh.
Duh. You just did the be smart thing and you just figured it out. Can anyone think of a different function which is also an antiderivative? Yes, Calvin.
X cubed over 3 plus 2.
Yeah. Going bold with the plus 2. Yeah, he says, hey man, I can add whatever I want. How about 2 million? I heard him say 2 million.
That's too much.
It's too much. Yeah. So, does everyone see what's going on here? Yeah, however you differentiate, the constant disappears. In fact, I think my actual answer is that anything of the form x cubed over 3 plus c will, all of those functions of that form, when differentiated, will all give me little f. Yeah? Okay. So we actually refer to the antiderivative. There's not a single antiderivative. There are a bunch of them. And we call it a family of antiderivatives. Okay. So the family of functions which are antiderivatives of x squared are all of the form x cubed over 3 plus c. Except maybe not. Are there any more? Are there other functions not of this form which, however, when differentiated, give me this function? Some weird thing. Yeah.
ln 2x squared, or 2 ln x squared. I mean, no, ln 1/2 ln x.
So she's coming up with some weird, funky stuff with ln. Can you like write that down on your paper and actually try to see if it works? Because I feel like it probably doesn't. 1/2 ln x squared. Yeah.
I think x cubed ln x.
X cubed ln x. Okay, try it. Differentiate that function. Do you get x squared?
Yeah, sorry, over 3.
Over 3. I don't know, they're coming up with weird excuses. I think they're all wrong.
It's 1 over x, when you have to multiply by x squared. Oh wait, product rule. Never mind.
Yeah, good discussion that we're having. By the way, I say the answer to this is no. Why? Someone talk to me. Calvin. And by no I mean, yeah. Yeah.
Oh, no.
Two of the same things, different things. The other way doesn't work. Does that make sense?
Okay, try it again.
Try it again.
Can you try saying it again?
Okay, so you can't differentiate two different big F's to the same little f.
Unless they're just differ by a constant.
Yes.
Yeah, that actually sounds like a theorem. Do you recall that being a theorem that we proved in this class?
Probably.
I
Like
think
how we did like everything.
that's how we did everything. Wait, okay, hold on. I'm going too fast and you're all lost now. Yeah, there's actually a theorem which says that if two functions have the same derivative, that they differ by a constant. We proved this.
Oh yeah, I remember that one.
Yes.
The graph and you drew it above.
We talked about the synchronized swimmers and stuff like that. There was a theorem that says that if two functions have the same derivative, then one has to be the other one plus a constant. Do you remember this theorem?
Yes.
We proved it. Do you remember how? Arun, how did we prove it?
With mean value?
Yeah, we did it on the mean value theorem day. It came as a direct result of another theorem. Kind of, yeah. What do we do? How do we prove this to me right now? Reprove this. Yes, good, excellent. Samin says, yeah, I remembered this. What we did is we constructed a new function h, which was the difference of f and g. Is this coming back to you? And then differentiated. If you differentiate this function, you get h prime of x equals f prime of x minus g prime of x. And by our assumption that these two functions have the same derivative, this is just 0 now, right?
Yes.
And this should now be ringing a bell. What can I say about a function if its derivative is 0?
It's a constant.
It is a constant function. So h is a constant function. And if h of x is just a constant c, but at the same time h is defined to be f of x minus g of x, then we conclude that f is just g of x plus c. Alright, so this is crucial. What this says is that if two functions have the same derivative, they must differ by a constant. And therefore, you guys will try to come up with weird crap. It's not going to work, right? The only functions which have a derivative of x squared are functions of the form x cubed over 3 plus c. Cool? Okay. More things. So I can write these in kind of interesting, weird ways. So over here I wrote it as f of x equals x squared. I asked for the antiderivative. I could also write it like this. I could also say dy dx is x squared. Okay, in other words, I'm talking about something whose derivative is x squared. Okay, and now I can do that thing which seems to be in fashion lately, which is treating these as differentials, and I can just like swing that dx over. So sometimes we do this, just like because. So dy is x squared dx, we say. And this is kind of like a transition to the notation for antidifferentiation, which is kind of interesting. And what we do is, if we want to antidifferentiate x squared, we write it as weird curly s thing, x squared dx. And we say the antiderivative of x squared is x cubed over 3 plus c. This weird curly symbol kind of looks like an S, and that stands for symbol of antidifferentiation.
Okay.
All right, that was a joke.
I know.
And we put the little dx in there just because. If the dx bothers you, either don't worry about it or think of it as a kind of marker which tells you what variable we are antidifferentiating with respect to. This is one way of thinking about it. Okay, good. Now that that's out of the way, let's just like do a million of these. So I'll call it out and then count to 4 and then give me the answer. What is the antiderivative of sine x dx?
Negative cosine x plus c.
Negative cosine x plus c. Yeah, all you have to do is rack through your brain and figure out, all right, give me a function which, when differentiated, would bring me back to sine. We tell you cool? Okay, good. Next, what is the antiderivative of e to the x dx? E to the x plus c. Good. Antiderivative of cosine x dx. Yeah, you did not wait 4 seconds, but that is correct. Sine x plus c. Cool? Cool. Am I going too fast or just right? Just right. Okay, what is the antiderivative of secant squared x dx?
And x plus c?
Yep. Yeah, because the derivative of tan is secant squared. Just have to wait 2 more longer seconds next time. Okay, can I just keep giving you a bunch more? Is anybody cool? Okay, antiderivative of x to the 4th dx.
Oh.
X to the 5th over 5 plus c.
Yup, x to the 5th over 5 plus c. How'd you get that? You're just smart duh. How about the so-called power rule for anti-differentiation in general? I don't care who they are, I don't want to talk to them right now. Go figure out what he wants and tell him I'll talk to him later. What is this?
1 over n x to the n plus 1 plus c.
Careful, over what?
Over
This has to be n plus 1.
plus 1.
Yeah, because like zoom zoom. Yeah, good. Okay, antiderivative of x to the... Is everyone okay with that? What's the antiderivative of x to the 2/3? They just like sign that for me. I don't care. No one cares about that. What is this? Yes, x to the 5/3 over 5/3. So it would be just like 3/5. By the way, if you're skeptical at any point, you can just differentiate and see if you get back where you started. Do you?
Yes.
Yeah, good. Everything's good. Okay, more. What's the antiderivative of secant x tan x? Cx. Secant x plus c. Good. What is the antiderivative of 1 over x dx?
ln x plus c.
Yeah, so you would think probably that the answer was ln x plus c, and that is kind of correct, but there are some, what's up?
Oh, there's also like
It's also the x to the -1. So.
Oh yeah, but that would be like garbage, right? Because if you try to do it, you'll get explode. So no, this is the correct formula. Yeah, because the derivative of ln is 1 over x. The issue here is like some domain problems, which is the fact that this is not totally right or not as good as it could be because this guy has domain only positive numbers, whereas this has domain all numbers. So there's a way we can just like fix it a little bit. If you will recall, what is the derivative of the ln of the absolute value of x? Remember we did this one day? I feel like we did. It is 1 over x. Mateo remembers. How do you deal with absolute values in calculus? You get rid of them basically, right? So you can just piecewise this out. Ln of the absolute value of x is just ln of x if x is positive, and if x is negative, then this is just the ln of negative x. Yeah? And then, says Mateo, if we differentiate piecewise, we end up with the derivative of ln x, 1 over x, if x is positive. But if x is negative, what's the derivative of ln of negative x? Yeah, it's like 1 over negative x back inside -1. So it's like also 1 over x. Just ringing a bell. Remember we like did this? Yeah. So answer, the derivative of ln of absolute value of x is just 1 over x full stop. And therefore, when I anti-differentiate 1 over x, I want to put absolute values in here because I want this to be like defined in as many places as possible. Are you okay with that? There's like more I could say about that, but like actually not really. All right, 3 more, and then we'll move on to something more interesting. What is the antiderivative of that? Or maybe I'll write it like this so I don't freak you out. So do these 3. Yes, I actually expect you to like remember these things and know them. Someone with good handwriting, grab a marker and get up there and write the correct answers.
The last one is secant.
Hope you mean arcsecant.
Arcsecant, sorry. Second one is arcsine. And then the first one is arctan. And then all the that's what I
Okay, what's the first one?
Oh my god.
What's the first one? Yeah, this is arctan. Arctan x plus c. Next one? Arcsine x plus c. Just a bunch of formulas that you learn once upon a time you need to know. This one? Arcsecant x plus c. Alright, are we basically good on this? Alright, what can you do with antidifferentiation? Answer, solve the problems of the world. But first, you can solve this problem. So find f if f prime of x is e to the x plus 20 over 1 plus x squared. And I better give you additional information, because if I just tell you the derivative of the function, that's not enough for you to figure out what the function is, as we've seen, right? But if I give you one more fact, for example, that f of 0 is 2, then you should be able to do this now. Go. Okay, done?
Yes.
You done? Okay, good. What do we do? I've told you that the derivative is e to the x plus 20 over 1 plus x squared. So if that's the derivative, well then the function must be an antiderivative of that, right? So an antiderivative of e to the x plus 20 over 1 plus x squared dx. And do we know how to anti-differentiate e to the x plus 20 over 1 plus x squared?
Yes.
Yeah, what is it?
E to the x plus 20 arctan x
Plus 20 arctan x
plus c.
plus c.
Wait.
And now I have to go figure out what c is. How do you figure out what c is? Well, you just use the so-called initial condition, right? If I plug in f of 0, I get e to the 0, which is 1, plus 20 arctan 0, which is 0, plus c has to be 2, and therefore c has to be 1. Follow? And since c has to be 1, I can now write the full function. The full function is e to the x plus 20 arctan x